Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our hearts to solve a paper 4. We call it ATP paper. This is also called alternative to practical. Today we have set our hearts to solve October-November 2023 4-2 paper. This paper 4 belongs from the zone 2. The time allowed for this paper is 1 hour. So let's start. And here we go. So on your screen, you can see the paper is showing up. This is the paper, October, November 2023, 4-2. The time allowed is 1 hour. These are the instructions. The total marks for this paper are 40 marks. And let's start. Question number 1. A student measures the spring constant K of a spring using two different methods. The spring constant K of a spring is a measure of the stiffness of the spring. The larger the spring constant K, the more difficult the spring is to stretch. So method number 1, the student measures the unstretched length of the spring to the nearest of 0.1 centimeter. A full-size diagram of the spring is shown in the figure 1.1. So it's a full-size diagram. The first part is measure the unstretched length. So you have to measure the unstretched length. Okay, so you have to measure the unstretched length L0 of the spring to the nearest 0.1 centimeter. The important thing is the word measure. And an important thing is this word, a full-size diagram. So what I will do with the help of the scale, I will measure this length. Measure means use your instrument to measure whatever the quantity they are asking you to measure. So here they are asking you to measure the length, and this is a full-scale diagram. So I will, with the help of the scale, I will measure it, and do not include the loops at the end of the spring in your measurement. So from this dotted line, I will measure up to this dotted line with the help of a scale. Okay. So I have done this and I found it to be 5.5 centimeter. So it is 5.5 centimeter. So the answer is correct. Okay. So the second part is the student attaches the spring to a clamp on a stand, suspends a 300-gram mass from the spring. The arrangement of the apparatus is shown in the figure 1.2. So here we have a stand. With that stand, with the help of a clamp, we have hung that spring here. And with that spring, we have hung a mass of 300 gram. Now you can see that the spring is little stretched. The student measures the new length L1 of the spring. The L1 is 17.6 centimeter. Calculate the extension E of the spring produced by the mass. Use the equation. So E is equals to L1 minus L0. You see, and now I know the unstretched length, that is L0, and that is 5.5 centimeter. And when you have hung 300-gram mass, so now the length of the spring, we call it stretched length, L1, and that is 17.6 centimeters. So we can calculate the extension. The extension will be L1 minus L0. So that will be, extension will be 17.6 minus 5.5, and that will be 12.1 centimeter. 12.1 centimeter. So that is the extension. 12.1 centimeter is the right answer, sir. Okay, then we have calculate the spring constant K1 of the spring. Use the equation. The K1 value will be 300 divided by E. So 300 divided by E is the value you just calculated. We will put this formula. So K1 will be equals to 300 divided by 12.1, and that will be 24.79. So you can also write it as 24.8 Newton per meter. 24.8 Newton per meter. Okay, so then we have it is important to avoid line of sight parallax errors when determining the extension of the spring. Explain what is meant by the parallax error and how to avoid the parallax error. You see, whenever you note down a reading from any scale, your line of sight must be perpendicular to that point on the scale from where you are taking the reading. If your line of sight is perpendicular to that point, then you will note down accurate reading. If your line of sight is not perpendicular to that point on the scale, then you will note down, due to the wrong positioning of the eye, you will note down an inaccurate number or reading. This is called parallax error. And how to avoid the parallax error? The line of sight should be perpendicular to the point on the scale from where you are going to take the reading. So this is my answer. So let's have a look. If the line of sight is not perpendicular to the scale, inaccurate reading will be noted. This is called the parallax error. This happens due to the wrong positioning of the observer. Line of sight with respect to the scale, I mean, the line of sight must be perpendicular to the point of scale from where the reading is to be noted. I hope you understand. So this is the marking scheme. I hope you can read it. Okay, so we are going to the method number 2. So that was the method number 1, in which they found the extension and then they found the K value 300 divided by E. So keep that in your mind. Now we are coming to another method of finding the spring constant. The student pulls the 300-gram mass down by a small distance and releases it so that the mass oscillates up and down. Measure the time t1 taken for 20 oscillations. So uh, he will pull the mass 300 gram downward, and then he will release it. Now that mass will vibrate, oscillate up and down, up and down. So you have to note down 20 time for 20 oscillations. The reading on the stopwatch is shown in the figure 1.3, and the reading given is 13.58 seconds. Record this time t1 in the table 1.1 to 1 decimal place. So you will note it down here, 13.58. Then this is the time t for 20 oscillation, 13.8. And then the mean time of 20 oscillations, you will add up these two times and you will divide it with the 2. You will get the average time or the mean time for 20 oscillations. Then we will find the time period. The time period will be, you divide this average time for 20 oscillations with the 20, and you will get the time for one oscillation, and then you will square that time. So this is how you do this. The student measures the time for the 20 oscillations once more. Okay, so let me show you. I have done this in the table, and here we go. So it is 13.6. It's approximately 13.5, so it's supposed 13.6, 13.8. So when you add these two and you divide it with the 2, you get 13.7. When you divide 13.7 with the 20, you get the time for one oscillation, that is 0.685 seconds. And then you square it, you will get 0.47, 0.47. So I hope you understand how we have done this table. So let me show you. So these are the readings, 13.6, and then you have 13.7 seconds, and these are the time which are coming up. Okay. Then he says the student measures the time for 20 hours once and more, records the time t2, calculate the mean. We are done with this. The mean period of the oscillation is the mean time taken for one oscillation, capital T. That mean period, capital T, of the oscillation is the mean time taken for one oscillation. Calculate that mean period and calculate the value of t square. Record all your values in the table. So I hope you understand we have done that. And you can check at this marking scheme also. Our answers are right. Okay, so this is how you do it. Hopefully you can see this. Okay, Then he says use your value of the t square from the table 1.1 to calculate the spring constant K2 of the spring. Use the equation. So here we are using K2 is equal to 11.8 divided by t square. So t square value I have already noted. So I am going to just use that value and we will find the K2. So here we go. The value, you can see K2 value will be 11.8 divided by 0.7. T square value was 0.47, 0.47, I said 0.7, 0.47. So when you divide 11.8 with the 0.47, you get 25.1. So the spring constant K2 is 25.1. So yeah, our answers are right. Okay, this is the calculation. Okay, in the C part, he says, explain why the value for the mean period T obtained by measuring 20 oscillations twice is more accurate than the value obtained by measuring one oscillation twice. You see, the time period for one oscillation is very short or small time, you can say. And when you will be using a stopwatch, you obviously you have to start the stopwatch, you have to stop the stopwatch. And if you directly try to measure the time for one oscillation, because that time for one oscillation is very short, so whenever you start, whenever you stop the stopwatch, the human reaction time is involved in this. So because the time you are measuring is very short, then so the human reaction time will be a larger part of that measurement as compared to that measurement. But when you measure the time for 20 oscillations, that duration is quite large as compared to the time duration for one oscillation. And so the human reaction time compared to the time for the 20 oscillations is relatively percentage wise is less. So its effect on the measurement reduces when you take the time for 20 oscillations. So I hope you understand this is my explanation. So my answer is timing 20 oscillations reduce the effect of human reaction time error on the reading. So hopefully you understand. Let's see what the marking scheme says. It says reduces the effect of reaction timing error, reduces the percentage error, uncertainty. The reaction time error is spread over 20 oscillations. So I hope you can write a better answer. So and remember one thing, the student, my students always surprises me. They can write even better answers. We just provide them a path, a guidance, that's it. So the magic is with the students. Question number 2 on your screen. He says, a student investigates the rate of cooling of water at the top and at the bottom of a beaker of hot water. So they are going to measure the cooling rate. Let's say you have a beaker of hot water and they will check the cooling rate in the upper surface of the water, and then they are going to measure or they are going to investigate the cooling rate at the bottom level of that hot water. Interesting. The student measures the room temperature, and that is theta R, and that is 22.5 degree centigrade. So remember this, the room temperature is how much? 22.5 degree centigrade. Pours 200 centimeter cube of the hot water into a beaker. Lowers a thermometer into the beaker until its bulb is just covered by the hot water. So as shown in the figure. So they have kept they have dipped only the bulb of the thermometer. So now they are going to investigate the cooling rate in the top layers of the water in that beaker. So here you can see in the diagram, and he says wait for approximately 30 seconds, starts a stopwatch and reads the thermometer. The temperature on the thermometer at the time t equals to 0 is shown in the figure 2.2. So record the temperature reading at the time t equals to 0 to the nearest of 0.5 degrees centigrade in the table 2.1. So this is the table 2.1. Here we have to note down that temperature. So how much is this thermometer showing? The temperature here is, I think, this temperature is, this is 81, 82, 83, 84, 85. This is 86. This is between 85 and 86. So it is 85.5 degrees centigrade. So the temperature shown on this thermometer is 85.5 degrees centigrade. So I will note down that temperature here. Let me show you. So I have noted down that temperature 85.5 degrees centigrade. So 85.5 degrees centigrade. This is question number 2. You can see that our answer is right. Okay. So now they are asking, explain why the student waits for 30 seconds before reading the initial temperature of the hot water. You see, when you have dipped the thermometer into the hot water, the bulb of the thermometer into the hot water, you give it some time. For example, you wait for 30 seconds. Why you do that? Because you allow the liquid that is in the thermometer to react to that temperature of the water, and you give it time so that liquid in the thermometer can expand, and you give it time so that the thermometer can respond to that temperature. That thermometer can show the temperature which it is recording. So that is the reason why we wait for 30 seconds. He waits to allow liquid in thermometers meter to expand and show the reading of the temperature of the hot water. Yeah. So you can read this marking scheme here also. So now we are going to the next part. I hope you understand my answer. This is question number 2B part. The student waits for 3 minutes. So that hot water, the bulb of the thermometer is in the top layer of the water. And he says, the student waits for 3 minutes, reads the thermometer and records the new temperature reading in the table 2.1. The student then, so whatever the temperature after 3 minutes is 78.0. Okay. The student then removes the thermometer from the beaker and pours the water away. Repeats the procedure in the A part, but lowers the thermometer into the beaker so that the bulb is just above, but not touching the bottom of the beaker as shown in the. Now, the bulb of thermometer has gone to the lower layers of the water in the beaker. Okay, if you compare here, it is in the upper layers of the water, but now the bulb of the thermometer is here. It's near the bottom of the beaker. Records the initial temperature and final temperature of the water as shown in the table 2.1. So at the bottom, the initial temperature is 86.0 and the final temperature is 77.0. Okay, after 3 minutes. Okay, after 3 minutes, at the bottom of the water, initial temperature is 86.0 degrees centigrade. After 3 minutes, the temperature is 77.0 degree centigrade. Okay, calculate the average rate of the cooling P at the top of the hot water and at the top of the beaker. Use the equation. Average rate of cooling is decrease in the temperature of the water divided by the time taken. So we can find the decrease in the hot water. So this is the initial temperature and this is the final temperature of the hot water at the top surface of in the top layers of the water. So you subtract them and you divide it with the time. You gave it 3 minutes, so you divide it with the 3 minutes. So you can see 85.5 degree minus 78.0 degree, and you have given it 3 minutes. So the rate of the cooling will be 2.5 degree centigrade per minute. 2.5 degree centigrade degree centigrade per minute. Okay, so this is my answer. So you can see. Okay, so now we are going to the next. So you have to note down the reading. You have to note down the what you call it, the unit. Then the second part is use the data in the table 2.1 on the page 7 to calculate the average rate of cooling. PB means the rate of cooling at the bottom of the water of the hot water at the bottom of the beaker. Okay, so I'm going to use these two readings. I will find the difference of the temperature, the drop in the temperature of the water, and obviously the time is still the same, 3 minutes, and we will see how much is the temperature and how much is the rate of cooling. So 86 minus 77 divided by 3 minutes, so 9 divided by 3, so that is 3 degrees centigrade per minute. 3 degrees centigrade per minute is my answer. So you can see this answer is right. Okay. So the next question coming up on your screen, he says, use your answer to the B first part and B second part to suggest why a hot liquid should be stirred before measuring its temperature. This is a basic, simple method that whenever before you measure the temperature of the a body of water, hot water, suppose you stir it. Why you stir it? Because you want to make sure that throughout the body of the liquid, the temperature is uniform. You make sure that the heat is distributed uniformly throughout the liquid, or you can say the temperature is uniform throughout the liquid. To make temperature of the water uniform throughout the water body or the water, you can see this is the marking scheme. This is what the marking scheme has to say. You can pause the video. You can take your time to read this marking scheme. Okay. Then we have, he says, suggest, sorry, this is the C second part. State one way in which the apparatus in this experiment is arranged to make it easy to read the thermometer more accurately. Okay, you see, if you look at this diagram, you see the reading is quite near to this clamp. Even in this diagram, the reading is quite near to this clamp. So another good thing, one good thing you can do is that you can make sure that you use a longer thermometer. When you use a longer thermometer, your clamp will be not near to that point from where you are taking the reading, because it's possible that the reading might enter, maybe reach that level where the clamp is. Okay, so this is one suggestion. Use a longer thermometer so that the jaws of the clamp do not hinder the reading from the scale, from the observer. Actually, I said I wrote from the scale. Can get close to the thermometer scale to read it. Thermometer is held steady in a clamp or stand. Scale can be rotated in the clamp to face the observer. Thermometer is long enough to be clamped without jaws obscuring the scale. Obscuring the scale. Instead of saying the hinder the reading, obscuring the scale is the better word. Okay. He says, D part, he says, the experiment is repeated to check the results, suggests one variable that must be kept constant. You see, there are so many things which should be kept constant. The beaker should be same, the amount of water should be same. We hope that the initial temperature of the water should be same. The most important is that which directly affects the, the cooling rate, and that is the room temperature. The room temperature must be kept the same. So I will have to write only one. Room temperature must be kept the same. So there are so many possibilities given here. So you only have to, give there only one reason. You can read them all. You can pause the video if you want time more on this marking scheme. The student leaves the thermometer in the hot water and waits for 30 minutes. Now he's saying 30 minutes. Before reading the thermometer again, predict a value for the temperature of the hot water in the beaker. We hope that in 30 minutes, the water will cool down to the room temperature. So probably the temperature will be 22.5 degrees centigrade. Remember, I encircled that temperature, which was room temperature, 22.5 degrees centigrade. This is our suggestion. So the water will cool down to the room temperature. Okay. So we are on the question number 3. He says, a student investigates how the potential difference V across the terminals of a power supply changes as the current I in a circuit changes. The student assembles the circuit shown in the figure 3.1. So here you have a power supply. Here is a voltmeter connected parallel to the power supply. Here we have an ammeter, which will tell you the amount of current flowing through this wire. Here we have a crocodile clip. The wire is attached on a meter, so you can measure how much length of the wire you are using in the circuit. So this is a flying lead. A part. A student closes the switch and observes the reading V naught of the voltmeter. The reading is shown in the figure 3.2. So you have to tell how much is this reading. 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9. So most probably the V naught reading is 2.9 volt. 2.9 volt. So here we got 2.9 volt. Okay. The student then connects the crocodile clip to the resistance wire at a distance D equals to 100 centimeter from the end X. So they are talking about this diagram. This is the end X. So they connected this crocodile here at 100 centimeter mark. Record the potential difference V across the wire as V equals to 2.3 volt. Records the current I in the wire. Open the switch. The reading on the ammeter is shown in the figure. So this is that reading. So let me tell you how much is this reading. Record the ammeter reading I. Okay, very simple. This is 0.5, this is 0.1, 0.2, 0.3, 0.4, 0.5. Okay, so this is 0.3, 0.31. Yeah, 0.31 is the reading. The reading is 0.31. So note it here, 0.31. The reading is 0.31 ampere. So our answer is right. Okay. C part is the student closes the switch, repeats the B for the values of the D 80 centimeter. Then he put the crocodile clip on 80 centimeter mark, then 60 centimeter mark, then 40 centimeter mark, then 20 centimeter mark. The student's results are shown in the table 3.1. Complete the header of each column. Okay. The distance here, that will be in centimeters, volt will be in volt, V, you write here. I will be in ampere, so you will write here a capital A. Here, when the length is 200.3, the V value is 2.3, the I value is 0.31. Note it here. Okay, so let me show you. I have done this. This is that table. Okay. So, okay. This is my table. Okay. Then he says, on the grid provided in the figure 3.4, plot a graph of V on the y-axis against I on the x-axis. Using the data in the table 3.1, start both axes from the origin. Draw the best fit straight line. Okay. So here that graph is given. I will be on the x-axis and the V will be on the y-axis. We have to start it from the 0, 0. So our I value is going from 0.37 to 0.88, and the V value is going from 1.2 to 2.3. So I've done that. So let me show you that. So you can see I have graduated here the scale on the x-axis and y-axis. And the grid is 2 centimeter represents 0.2 ampere on the x-axis, and 2 centimeter on the y-axis are representing 0.5 volt. So here I will have 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. Then I will plot this table. So I is on the x-axis, the V. I will take on the x 0.3, 0.31, 2.3. I will plot that point. 0.37, 2.2, 0.45, 2, 0.60, 1.7, 0.88, 1.2. So these points I have plotted. Let me show you. So this becomes too large, I think. So you can see I plotted this point, this point, this point, this point, and this point. Then I have drawn the line of the best fit. You can see whenever you draw the line of the best fit, you try to draw the line in the same pattern, and you try to make sure that the number of the points above the line and the number of the points below the line are same. Okay. So this is now the line of the best fit. I hope you understand this, and you can read this marking scheme as well. Pause the video, you can take out your time. So hopefully you understand. Then he says, after this he says, the gradient of and the gradient m of your line is numerically equals to the resistance r of the power supply. Calculate the gradient of your line, show clearly on the graph the values you chose, and show your working. So this is the E first part. Okay, so I will take this point. For example, this point is 0.2 comma 2.5. I will take this point. It is 1.2 comma 0.6. The working here, I will complete this right angle triangle by joining these 2 points. So this is my rise, this is my run. If you divide the rise with the run, you get the gradient of that line, and very easily you can find the gradient. I hope for O-level students, finding the gradient of a given straight line is not a big deal. Okay, so I have taken 0.2 comma 2.5 and 1.2 comma 0.6. So the gradient will be y2 minus y1 divided by x2 minus x1. You can also say v2 minus v1 divided by I2 minus I1. So it will be 0.6 minus 2.5 and the whole thing divided by 1.2 minus 0.2, and it will be minus 1.9 divided by 1, and that gradient is minus 1.9. So just ignore that negative sign because this gradient, because the gradient is basically equals to the resistance. So that will be 1.2 to 2. So our answer is right. This is how you do it. The intercept between the y-axis and your line is the electromotive force V naught of the power supply. Extend your best fit line to meet the y-axis and write down the values of the V naught. Now the V naught from the is the y-intercept. So you see what does that mean? That means when I extend this line, when this line cuts the y-axis, you just have to note down that value. This is 0.85. 0.85. So I will note it down. This is not 0.8. This is 2.85. Sorry, I said 0. This is 2.85. Sorry. 2.85 volts. So V naught is 2.85 volt. So candidate's intercept value. So our answer is right. Okay. I hope you understand these wordings. Then he says, compare the V naught in the A part with the V naught. V naught in the A part was 2.9. And the V naught here we got is 2.85. Compare the value V naught in the A part with the value of the V naught you obtain from the graph in the E second part. This is the F part we are doing, by the way. Two quantities can be considered to be equal within the limit of experimental accuracy if their values are within the 10% of each other. State whether your results show that the two values obtained for the electromotive force are the same. Support your statement with a calculation. So I will show the calculation. In the A part, the V naught value was 2.9. So I will find 10% of 2.9, and that 10 by 100 into 2.9, that is 0.29. So add 0.29 into 2.9, you get 3.19. And from 2.9 subtract 0.29, you get 2.61. So my second value of the V naught, which was in the E second part, that was 2.85. And that 2.85 is within these two limits. So that means both the values agree with each other. That means, so both values 2.9 volt and 2.85 volt are same. 2.85 volt is not written. It is within the limit of experimental accuracy. So they are same. I hope you understand. This is the answer. Okay, the next G part of the question number 3, he says, another student decides to connect the crocodile clips in the figure 3.1 so that there is only a very small length of the resistance wire included in the circuit. The teacher tells the students not to do this. suggests one practical reason why the values of the D less than 20 centimeters should not be used. You see, when you use a length whose length, a wire whose length is less than 20 centimeter, its resistance becomes lower. When the resistance is lower, the current coming from the supply increases. And if the larger amount of the current is passing through the wire will overheat. This can be one reason. Another reason, a good reason can be if the distance between the X point and the point where you have put the crocodile clip, that becomes very small, that D value is very small, then the two crocodile clips might touch each other. So, so let me show you what I have written. So you can see here my answer. Smaller length of the wire has low resistance, which draws larger amount of the current from supplies. This causes the wire to become hot. This can cause the wire to become hot. So this is our answer. So let's see. This is the marking scheme. You can take out your time. You can pause the video and take time and read the question number 3G part. Okay, so question number 3H part, he says it's now a 2 marks question. It is possible to change the potential difference V by using a variable resistor rather than using different lengths of the resistance wire. Complete the circuit diagram in the figure 3.5 to show how the variable resistor is connected. So if instead of using that wire, crocodile clips, everything, you just remove them, you use a variable resistor, and you can change the resistance of the variable resistor. The V value will change, the I value will change. Okay, so how you do this? You see, I have connected the voltmeter parallel to the power supply. The ammeter is connected in series with the variable. This is the electric symbol for the variable resistor. So you, by changing the resistance of this variable resistor, you can get the different values of the I and the V. So this is my answer. Okay. So we are going to the next question. The next question is question number 4, and this is a planning question of the ATP, planning an experiment. Question number 4. A student investigates the average speed of a trolley moving along a horizontal bench. A trolley is placed on a ramp and released from rest. Some of the apparatus used is shown in the figure 4.1. So basically we have a stand here. Here we have a clamp. It's holding a ramp. So the ramp is inclined. So here you release the trolley. The trolley comes here. So from this bottom of the ramp, it moves and it stops somewhere here. Okay. The stopping distance of the trolley The stopping distance of the trolley is the distance moved by the trolley from the bottom of the ramp until it comes to rest. Plan an experiment to investigate how the average speed of the trolley along the bench until it comes to rest depends upon its mass. The mass of the trolley, I mean. The average speed of the trolley can be calculated using the equation shown. Average speed is stopping distance divided by the time. In your plan, you should explain briefly how to carry out the investigation, stating any other apparatus needed. State the key variables to keep constant. Draw a table with the column headings to show how to display the reading. You are not required to enter any readings into the table. Explain how to use your readings to reach a conclusion. So here we have to, plan an experiment. Okay, so the plan is very simple. Use a balance to measure the mass of the trolley, and if you put a mass on the trolley, means the mass. Or you can, because the trolley will be in all the experiments, same. You can measure the mass which you put on the trolley with the help of a balance. Release the trolley from this ramp. Note down the time when the trolley leaves this bottom of the ramp, and when the trolley stops, note down how much time it takes to stop. And measure with the time, obviously you will measure with the stopwatch, and This distance, the trolley moves on the horizontal bench, measure it with the help of a measuring tape. Okay, so then divide that distance on the trolley moved on the horizontal bench with the time it took before it stops. From the bottom of the ramp to the point where it stops, note down how much time it takes to cover that distance. Then divide that distance by the time, and you will get the average speed. Now, you can repeat this experiment, then do this experiment again, but this time increase the mass on the trolley and do the same procedure. Okay, so the so what are the variables which you have to keep constant? You see, the length of this ramp should be the same in all your experiments while you are increasing your mass. Okay, the trolley should be the same, and the angle of the ramp, or you can say the height of the ramp, should be the same. This bench should remain the same, and the point on the ramp from where you release the trolley, that should be same. Okay, then they ask us to write what table. You will make table. In first column you note down the mass on the trolley. In the second column you note down the distance moved on the horizontal bench. Then you take the time taken, that will be in seconds, and then you calculate, make a column for the speed, that will be, you divide the distance by the time, you get the speed. And then at the end, how you will conclude, how you will come to a conclusion, the relationship between the mass of the trolley and the average speed. You will draw a graph. You will describe that, draw a graph by taking the mass of the trolley on the x-axis and the speed of the trolley, the average speed of the trolley on the y-axis, and draw a graph between these two. And by looking at the shape of the graph, you will be able to conclude that what is the relationship between them. Hopefully you understand what I'm saying. I have written this. Use balance to measure masses which will be placed on trolley. Release trolley from the ramp. Note the time trolley takes from bottom of ramp until it stops on horizontal table with the help of a stopwatch. Measure the distance trolley moved from bottom of ramp to the point where it comes to rest with the help of measure tape. Note mass on trolley, distance moved by trolley, and the time taken in the table, and calculate in the table, and calculate speed by dividing distance by time. Repeat the same procedure by changing the mass on the trolley. Every time you repeat this experiment, use same length of the ramp, same angle of ramp, also keep same point on ramp to release the trolley. And this is the table which I think you have to draw: mass, distance, time, speed. Draw a graph by taking the speed on the y-axis and mass on the x-axis. By looking at the shape of the graph, you can decide the relation between mass and speed of the trolley. So let's have a look at the marking scheme. This is the marking scheme showing up for the question number 4. You can pause the video and you can take the time to read this marking scheme. I hope that you have understood this planning question, and this planning question was added into our syllabus in May June 2023 exam, and you do not find too many planning questions in your ATP Red Spot books. So, my dear students, we have reached the end of this paper, and yeah, we have reached the end of this paper. So, my dear students, thank you very much for watching this video, and remember this thing: we are not a scholar of anything. We are a humble student. I am basically a humble student of physics, and I only facilitate people to study. Okay, so It's possible that I might make a mistake. Uh, being a human, it is possible. So don't take it too seriously. Okay. So always check the marking scheme. It's a must. Never, whenever you write an answer, you check it from the marking scheme. Okay. So so that you know that what the Cambridge wants from this answer. So if you like this video, if you think this video is helpful, please share the link of this video. Please like this video. Share the link of this video onto your on your WhatsApp, on your Facebook, on your Twitter, on your X, on your Instagram, on your TikTok, because when you do this, this helps me to promote my channel. Thank you very much. I think it's a great blessing for me that I can make these videos, which can help some students, a lot of students around the globe. So thank you very much. Have a good day. God bless you all.